Hi, I'm Jeff Groh and this is Calculus 2. Today we're going to talk about alternating series. We'll begin with a definition. To this point, we've assumed that all of our series have terms that are positive. However, it's possible that some of the terms could be positive and some negative. If the series has terms that switch between positive, negative, and so on down the line, then the series is said to be alternating. So that's a special kind of series. So an alternating series has the form, the sum as k goes from 1 to infinity of -1 to the k a sub k, or the sum as k goes from 1 to infinity of -1 to the k plus 1 a sub k, where a sub k is positive. What is the explanation for needing one of two different forms? The answer is, in this first instance, when k is equal to 1, we end up with a negative first term. And then the next term is positive and negative and positive and so on. In the other form, when k is equal to 1, because the exponent ends up being 2, we have a positive first term. It doesn't matter whether you start with a positive or with a negative first term. What matters is that the signs change between positive and negative as you go down the line. Alternating series have some remarkable properties. In particular, we have what is called the alternating series test. Suppose, first of all, that we have a sequence of positive terms a sub k. That gets smaller. And in such a way that in the limit as k goes to infinity a sub k, you get 0. If we have a sequence of positive terms here that monotonically decrease to 0, then the alternating series that can be constructed from that, for simplicity, I'm just going to put -1 to the k. This argument also works if I have -1 to the k plus 1. Then this thing converges. I want you to think about this. When it came to series having positive terms, we showed that the terms going to 0 was necessary to get convergence for the series, but was not sufficient. The harmonic series had terms that went to 0, and they went to 0 in a monotonic fashion, but the harmonic series diverge. For alternating series, all it takes to demonstrate convergence is that the terms tend monotonically to 0 in absolute value. This is like the best convergence test ever. All you have to do is identify that you're dealing with an alternating series. Once you see that, just check to see that these terms go monotonically to 0, and you've got it. It converges. It's about as simple as it gets. Being such a remarkable test, we have to see the proof of this one. And in particular, we're going to begin by looking at the sum as k goes from 1 to infinity, -1 to the k plus 1 a sub k. We'll apply the proof to this particular case. That way we'll start off with a positive term when k equals 1. Let's look at the even partial sums. That's going to be a1 minus a2 plus a3 minus a4 plus a 2n minus 1 minus a 2n. Notice that we can associate these terms in the following way. And in that way, because a2 is smaller in magnitude than a1, this will be positive. And this must also be positive. And this is also positive. Every time we increment n, we end up with another 2 terms subtracted, but those differences are positive, which implies then that the sequence of even partial sums is monotone increasing. What is more, still looking at those even partial sums, we can group the sums in a slightly different way. We can group them by grouping these terms instead. So we'll have a1 minus a2 minus a3. When we factor a negative out from here, we'll get a subtraction. We'll have, if we distribute the negative, a negative a2 and a positive a3, just as above. We'll have a 2n minus 2 minus a 2n minus 1, and then finally minus a2n. What do we observe from this? For each of these increments on n, we end up subtracting more from a1. a2 minus a3 is a positive value since a3 is smaller than a2. We're assuming the terms monotonically decrease to 0. So this difference is positive, and we're subtracting it from a1. So by subtracting a positive value from a1, we get something smaller. And then we get something smaller, and smaller still. That means that the sequence of even partial sums is no worse, no bigger than a1. That means the even partial sums, we said already, is monotonically increasing, but it must also be bounded. We talked about the Weierstrass theorem back in the section on sequences. The Weierstrass theorem said that any monotone bounded sequence converges. So, by the Weierstrass theorem, the even partial sums as a sequence converges to, say, some value s. Let's look at the odd partial sums. This odd partial sum, s2n plus 1, adds one more term to s2n. So it's going to be equal to s2n, but it's going to be equal to that plus that one last odd term. Now, we know that these terms, one of the hypotheses of the alternating series test is that these terms must tend to 0. So if all of the terms tend to 0, then surely the odd ones will. So this is a sequence that converges. We already know that this sequence converges by the Weierstrass theorem, which means that the sequence of odd partial sums is equal to the sum of two convergent sequences. By a theorem from the first section of this chapter, it follows then that since this is the sum of convergent sequences, it too must converge. Since this is the sum of convergent sequences, it must converge. Also, if we look at the limit as n goes to infinity of s 2n plus 1, that must be the limit as n goes to infinity of s 2n plus the limit as n goes to infinity of a 2n plus 1. We know the terms must go to 0 as a hypothesis of the alternating series test, and these go to some value s. So the odd terms go to the same limit as the even terms. It follows that the nth partial sums generally tend to the same limit s. By this I mean the limit as n goes to infinity of s of n equals s. And that is the end of the proof. There's a classical example that you need to be aware of. This series looks a lot like the harmonic series. What makes it different is that it's alternating in sign. This is going to be 1 minus a half plus a third minus a fourth, and so on. Notice that in this particular case, a sub k is 1 over k, which is monotonically decreasing to 0. How can you tell it's monotonically decreasing? Well, it decreases like 1 over x. But you can do better than that. For a technique that you can use later on down the line, we can take the derivative. The derivative of 1 over x, you know, is negative 1 over x squared. So here we'll get negative 1 over k squared. The derivative is less than 0, which means it is decreasing, monotonically decreasing. Also, in the limit as k goes to infinity of 1 over k, you get 0. So this series satisfies all of the hypotheses of the alternating series test. By the alternating series test, this series converges. Note that this series, we said, looks a lot like the harmonic series. It's just alternating. Guess what? This series has a name, and it's famous. It's famous as the alternating harmonic series. Everyone knows that the alternating harmonic series converges. If you see this series in the future, you can claim that's the alternating harmonic series, and hence it converges. But there's something else about this series you need to be aware of. A series is called absolutely convergent if in absolute value it converges. We've seen that the alternating harmonic series converges, but in absolute value it reverts to the old harmonic series, and the harmonic series does not converge, it diverges. That means that the alternating harmonic series is not absolutely convergent. All of the P series that you've seen to this point, those are absolutely convergent. However, the alternating harmonic series diverges in absolute value, and so it converges, but it's not absolutely convergent. If the series converges, but not absolutely, it is called conditionally convergent. Conditionally convergent series have a lot of very interesting properties, as we'll see. One in particular is that you can rearrange the terms of a conditionally convergent series in such a way that it will converge to any number, any real number that you wish. What does that even mean? It means that in the context of conditionally convergent series, the commutative law of addition, applied infinitely, is false. One of the classic things that you learned way back in first grade, that it doesn't matter what order you add, you'll get the same sum. That's no longer true if the series is conditionally convergent. It's easy to show, and we will at some point, that there is a rearrangement of the terms of a conditionally convergent series so that you can make the series converge to anything you wish. Since I mentioned the failure of the commutative law of addition for these conditionally convergent series, let's go ahead and show that. Suppose that you have a conditionally convergent series. What does that mean? Well, one thing it means is that the partial sums have to go to some finite limit, but in absolute value, the partial sums don't converge. This has to diverge. Let A, K, J be the positive terms and A, K, J hat the negative terms. Because the series of absolute values of these terms goes to infinity, then either the sum of the positive terms or the sum of the negative terms must go to infinity by themselves. However, since the sum of the terms with these mixed together goes to some finite value, that means that the sums of the positive terms and the sum of the negative terms must both go to infinity in order to balance out. Otherwise, the sum of the terms would go to either plus infinity or to minus infinity when you add up all these negative terms. Suppose we wish the sum to be rearranged to obtain a value of L. We want to rearrange the sum so that the terms add up to L. Here's our strategy. Add from the positive terms until the partial sum is above L. Once you get above, add from the negative terms until you're below. Since the original series converges, the divergence test tells us that the terms must tend to zero, which means we'll get closer and closer to that limiting value L. We'll have the limit on k of sk is equal to L. Not all alternating series are like that. This is an alternating series. It has terms that monotonically decrease to zero. It converges by the alternating series test. Remember, there's a couple things you have to check for the alternating series test. First, the derivative of 1 over k squared is negative 2 over k cubed, which is going to be less than 0 for k that are elements of the set of natural numbers, which means that we get monotonically decreasing. Second, in the limit as k goes to infinity, 1 over k squared, you go to 0. So the terms monotonically decrease to 0. By the alternating series test, this series converges. But it does more. In absolute value, we get a p-series. P is 2, and that is strictly greater than 1, and therefore this converges. If the series converges in absolute value, then it is absolutely convergent. A series that is absolutely convergent will converge to the same sum no matter how you rearrange the terms. In other words, the commutative law of addition works just fine, but only if the series is absolutely convergent. If the series is conditionally convergent, there will exist rearrangements of the terms so that the sum will end up adding up to whatever value you choose. Not true in this case. There's another important feature of alternating series. If we're dealing with an alternating series, and I'll just use k because I'm lazy and don't want to write k plus 1, or both of those cases. So we have an alternating series, terms that monotonically decrease, to 0. The alternating series test tells us this will converge. If the sum is equal to some value L, then when you take the difference between the nth partial sum and the overall sum, that's going to be no more than the very next term. What does this mean? This means that if you chop an alternating series off at some value of n, how far off are you from the ultimate sum? You're going to be only an approximation because you're truncating the series by chopping off the tail and only adding up the first n terms. How far are you off? No worse than the very next term. I'm going to begin the proof by defining some notation. If we have an alternating series, has some s, we'll set the remainder to be s minus that nth partial sum. This is what is left over, the gap between the nth partial sum and the actual sum of the entire series. What we want to show, and WTS is the standard mathematical notation for the phrase want to show, we want to show that this distance is no worse than the very next term. The error that you get in approximating the sum of an alternating series by truncating at the nth term is no worse than the magnitude of the very next term. Continuing with the proof, you can see that Rn is going to be the sum minus the nth partial sum, and if you keep in mind this is the total sum, and this is the nth partial sum, that what you get is the sum from n plus 1 to infinity. That is equal to the following. Some infinite sum, but starting here, we can factor out this negative 1 to the n plus 1, and that negative 1 to the n plus 1 can be separated off. And then canceled off. We can rearrange that sum in the following way. By grouping the terms, except for this first one, in pairs and factoring a negative out. Because we assume that the terms are getting smaller and smaller in magnitude, these differences will all be positive, and we're subtracting those positive values from this first term, which means that we're going to get something less than or equal to an plus 1. And that is the end of the proof. I want to show you how this works. Let's look at our alternating harmonic series. It's possible to prove that the alternating harmonic series adds up to the natural log of 2, and we will be able to prove this in the next chapter. But for right now, take it as a matter of faith that the alternating harmonic series adds up to the natural log of 2. Crunching that number on my calculator, I get 0.693147. Note that the original series is 1 minus a half plus a third minus a fourth, and so on. What is 1 minus a half? 1 minus a half is 0.5. How far off are we from the actual value of the sum? Well, the remainder is no worse than a 3, which is 1/3. And we are certainly no more than 0.3 off from our actual answer. In fact, we're about 0.19-ish off. Are we better off at S9, which is 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth plus 1/9? That adds up, according to my calculator, the sum is 0.746-ish. Still not very good, but we're closer. We're about 0.05 off from our actual value for the sum now. A natural question might be, how many terms are required in order to estimate the sum of the entire alternating harmonic series to within, say, 5 decimal points. How many terms do you need? That means our tolerance for error is going to be 5 times 10 to the negative 6. We have to be off by less than 5 in the 6th decimal place. By the remainder theorem, we need an plus 1 to be smaller than our tolerance for error. But an plus 1 is 1 over n plus 1, since a sub k was 1 over k. Taking the reciprocal on both sides reverses the order of the inequality. And then we move the 1 over. We have to have at least 1 plus 1 over 5 times 10 to the negative 6. Well, how much is that? My calculator tells me that we have to have more than 200,001 terms. That's a lot of terms. not impossible. We've already done computations using the computer that involved more than 1,000, more than 1,000,000 terms. 200,001 should be no problem, but that's still a lot of terms. One lesson that you can obtain from this example is that these alternating series, though they may converge, like the alternating harmonic series converges to the natural log of 2, they converge slowly at times, quite slowly. I have to go way out there before I'm to within 5 decimal place accuracy, more than 200,000 terms. There's an important question that we've left unanswered to this point in the development of our theory. If a series is absolutely convergent, then it converges. The converse of this theorem is not true. There are series that converge, but do not converge absolutely. However, if a series does converge absolutely, it must converge. To prove this, consider that 0 is less than or equal to a sub k plus the absolute value of a sub k. If a sub k is negative, the absolute value will cancel this and you'll get 0. If a sub k is positive, then both of these terms are positive and you'll get something greater than 0. What is more is that this is less than or equal to twice the absolute value of a sub k. It follows that the partial sums satisfy this sequence of inequalities. Now, this thing converges in the limit as n goes to infinity. You get some finite value. Since this is a series having positive terms, the partial sums must get bigger and bigger and bigger, but they have to be bounded, which means that this series of partial sums is monotone and bounded and therefore converges. To prove that the original series converges, we'll play a little game. A sub k is going to be a sub k plus the absolute value of a sub k minus the absolute value of a sub k, where we're going to group these right here. Since this series converges, and since this series converges, that implies that the series involving a sub k also converges, because it's the sum or the difference of two convergent series. And we know that if we add or subtract convergent series, we get a convergent series. And that is the end of the proof. As an example, this series converges absolutely in absolute value. You get the series 1 over 2 to the k, because in absolute value, the negative ones are all going to go away. This is a geometric series with common ratio equal to 1/2. Since that's less than 1, that implies in absolute value the series converges, and since it converges in absolute value, It converges absolutely, because that's what that term means. We now also know from the last theorem that since this series converges absolutely, it converges. But we could have had that from the geometric series test as well. What about the sum as k goes from, let's say, 2 to infinity, negative 1 to the k, divided by the natural log of k? I started at 2 because if I started at 1, the natural log of 1 is 0, and I'd end up with the division by 0. Does this converge, and does it converge absolutely, or does it converge conditionally? On all of our alternating series, I want you to state whether or not the series converges, but I also want to know, does it converge absolutely, or does it converge conditionally? So, to show that this series converges, we can use the alternating series test, the best test on the planet. A sub k in this case is 1 over the natural log of k. We leave this off when analyzing these series using the alternating series test. We need to prove that these go to 0, and also that they go to 0 in a monotonic fashion. So first, we'll take the limit as k goes to infinity of 1 over the natural log of k. Since the natural log curve goes to infinity, 1 over infinity, this thing is going to go to 0. What about the derivative? Getting a negative derivative will imply that this thing decreases monotonically. We're taking the derivative of something that's in the form of 1 over, which has the form of negative 1 over that thing squared times the derivative of the inside using the chain rule. Since k values are taken from 2 or higher, this will be negative in that region, and hence this is monotone decreasing. We deduce then that the series converges. But we have not resolved whether or not the series converges absolutely, or if it converges conditionally. Note that the log function grows more slowly than y equals x, which means that ln of k is smaller than k. It follows then that 1 over the natural log of k is bigger than 1 over k, since this series is the harmonic series, and therefore diverges by the comparison test, the direct comparison test. The series of positive terms diverges. Since in absolute value the terms diverge, this series converges conditionally. That was a fairly complicated argument. First, we showed that it converges using the alternating series test. Then, we did a direct comparison to the harmonic series, which diverges. And that implies that in absolute value, this series diverges, and therefore it does not converge absolutely, it converges conditionally. In our next example, suppose we have the sum, as k goes from 1 to infinity of negative 1 to the k of 2 to the k divided by k squared. The way to analyze this is using the divergence test. 2 to the k blows up exponentially. K squared blows up quadratically, like a polynomial. Exponential growth beats polynomial growth every time. We can see that the limit as k goes to infinity of these terms, whatever it is not 0. That means this series diverges by the divergence test.